So my name is Rynge. Let me go back here. This session is really generally about workflows. I do work with multiple workflow systems. However, my home institution there, USC Information Sciences Institute, that's where Pegasus has been developed, part of the Pegasus development team. So I do a lot of Pegasus work. But in general, we are going to answer questions about workflows in general. So we get two questions beforehand. One is how Pegasus takes care of protected data. And the second one is have a few questions about feasibility of supporting workflow systems on a floating vessel. And the second one I think will be kind of interesting. The first one I can talk a lot about. So I'm going to kind of give an overview here. I've added a lot of slides from previous talks. But it also is a nice tie-in to a working group that we've been part of called the Trustworthy Data Group, a working group. And this is a lot of different members in this group, but it's driven a lot by Trusted CI and then CI/CoE pilot. And so currently, this is the state of this working group. The goal here is to really kind of define what is trustworthy data and how does it apply to researchers. So the first thing we did is that we did a community survey. And that's what you see up here. There's a link to the report, the scientific data security concerns and practices. And we had about 111 people responding. And the questions in that survey was, what is trustworthy data? What are the attributes of that? How does it apply to your position that you're in and your work? And at PERC 20, we then had a workshop where we presented the survey results and we had a discussion about it. And currently we're working on a guidance for science projects and cyber infrastructure developers guidance document. And this one is, I'm pulling a little bit from that just to kind of get started talking about protected data. Because the problem is, when people say, well, how do you deal with protected data? What is protected data? And it depends a little bit on and again, I wish that person was here to kind of help us define it. But it could be, for example, HIPAA data, right, or something like that, where you have sensitive data that you have to make sure that is not being exposed as part of the computation, right? And so in this list here, these are some of the attributes that we kind of trying to we think they fit into that guidance report. This again, it's a work in progress, so it's not, the list is just being developed as we talk, but I still want to put it here. And so if we talk about HIPAA data, for example, well, we talk about confidentiality, and we're talking about stewardship and methodology and things like that. We're not really talking about the data accuracy or integrity. Those are attributes that are important, but it's maybe not protected data. What I was going to say though is that in the realm of some of these attributes like integrity, reproducibility, and provenance, these are things that workflows are really, really good at, right? And I have a lot of slides talking about these here. Methodology stewardship, not really. Accuracy, this is more, it's actually part of methodology, I think, so maybe they should be joined. And then there's reputation, significance, availability, obviously important for workflow systems, but not something that we provide, and accountability. So, but if we focus on and I was going to say, right, like when we talk about HIPAA data, it's actually more of the infrastructure that we are computing on. Hey, Salak. Actually not connected. There we go. Hey, Salak. Welcome.
Thank you.
Did you post a question to us?
No, I was just checking if everything is under control in terms of security.
Perfect. Yeah. Okay. Perfect. All right. So we're currently talking about what. Well, the question we're talking about is how Pegasus takes care of protected data.
Okay.
Right. Right. So HIPAA data, I mean, it's a function of the infrastructure you're running on. So an example of this is, if you have a HIPAA compliant machine, or not compliant, what is the word? HIPAA. Well, anyways, if you have a machine that's been kind of okayed for HIPAA work, there's all these rules and things like that. So you kind of have to own, or it has to be very controlled environment. A lot of the times we're using Pegasus, we do remote compute, right? We maybe submit locally, and then we run it on either Open Science Grid, or we run it on a campus resource, or we run on something like Exceed, and all those, right? Like that. So the HIPAA problem is not a function of the workflow system per se, but more of the targeted resource. That being said, though, when we talk about more of these that we talked about, integrity and provenance and reproducibility, I'll talk a little bit about that. And it came out of a work we have done the last couple of years in Pegasus. So this is a presentation that we did last year at PERC 19. And the goal here was really to add better integrity protection into the workflow. We kept on having users that ran into data corruption and or problems in network and things like that. So we decided that maybe there's a better way of formalizing this and making sure that at least we catch this. And one of the interesting things with this project, when we started SWIP, was that we weren't sure that we were going to kind of see any real world examples of that. We thought that maybe we'll add all this integrity protection into the workflow engine, and at the end of the day, there won't be any errors caught. And I'll show you here a little bit later that we did catch stuff in the wild. Hey, welcome, David. How are you?
I'm doing pretty good.
Did you post any of the questions?
No, just here to see what you're saying.
All right. Well, we're talking about data, like how Pegasus protects data. Okay. So, and if you have questions, we'll deal them afterwards, right? So, I don't think I'm going to go through this whole presentation. There's a lot of slides. I'm going to jump around a little bit. But so here's a good example of what we're talking about data integrity, right? And it's actually kind of a short slide compared to, I think, the size of this problem. So one thing that we see is, that IT systems are not perfect. And we know this, right? We know this as a computing specialist. Like, there is no such thing as a bug-free software, right? And that goes for things like network switches, and that goes for things like data transfer tools or protocols, right? Like, well, they are pretty good, but they are not perfect. So, you could see bit flips and things like that in when doing data transfers, or even having data just sitting on disk. And the paper here has a few references to real errors as well. Another problem is data sizes, right? Like a lot of the protocols, TCP, by the way, included, they were not really designed for the data sizes that we have. Right? The checksum in TCP is kind of a weak, like a small checksum compared to the data amounts. And then we have the intentional threats, right? Where we have attackers and inside threats. The paper we wrote didn't really concern us much about those. They do exist, but it's almost the same as detecting it is the same as if it's software bug or an intentional change. So again, there was a few pointers on people seeing this. In case this is example of data sitting on disk and being corrupted, right? So they're talking about Wave 5 and physical disks seeing bit flips. And we also see it at transit, and this is an example where Exceed had an actual Brocade, which was one of the network vendors, had a bug in their package handling, and that ended up being corrupting data in transit. And similarly, we had a problem at University of Chicago during an upgrade where we could see data corruption as you know, corner jobs came back, and there was tar files, for example, that we couldn't untar because they were corrupted. So it was pretty obvious in that case that something was going on. And obviously software failures, I already mentioned that. So what do we do about this? Well, it turns out that the workflow system is a pretty well-suited system for tackling this problem. And the reason is that we're already kind of doing all these multiple steps. We already have ways of kind of inserting jobs or tasks into our processing. And so the real kind of fix here, and I think I have a better slide. Let me see. Yeah, okay. Well, we'll just jump here. So what we ended up doing is to add automatic integrity checking for all the data in the workflow. And the way we're doing this is that if we take this is a workflow, it's running here. Here's a remote compute site, a remote compute node that job is running on. And if we zoom in on this job, right, we're using this looking glass to look what's going on inside this little job. We see like even job looks like a workflow. There's multiple steps where, you know, we're pulling data in and we're pushing data out at the end. We see these two new here, like what is this? This is purple and pink. Those, the one that's right before the task here is an integrity validation, right? So before we do compute on the data, we calculate the checksum and compare it to a known checksum. And by doing so, we know that even before the computing starts, we know that we're doing computing at the right piece of data. And then when the task is done and we have new data products, we do the same, we do the reverse, right? We generate new checksums, we store them in our metadata systems that we later in a subsequent job, for example, can check the checksum on the produced data earlier. And if any of these checksums fail, well, it's a job failure in Pegasus. We stop, we retry the job. If that still doesn't work, well, we'll stop the workflow and not do, we'll not keep going from there. So we did a little bit of testing on this. There's a whole exogeny thing where we built a test bed and we kind of validated the approach. I'm not going to spend time on that here. But what I want to talk about a little bit is, you know, how big of an issue is this to people running workflows, right? And I'm going to just preface this with saying that the numbers I have on these slides are not maybe, you know, it's not an average, right? When we went looking for these problems, we kind of looked extra hard on workflows that were less protected than others. So what that means is, for example, we took an extra look at the large workflows with a lot of data transfers. That means, for example, running on Open Science Grid, just because of the distributed nature of that infrastructure, you know, you do extra data transfers. We also looked at unprotected protocols, and this is an important point because what happens is, as I said, TCP maybe is not great at doing this. There are collisions and things like that. But it turns out that as soon as you start using a protocol that is like cryptographically based for that data transfer, I'm talking about, for example, HTTPS like SSL or OpenSSH, or using grid FTP, anything that kind of has like a little bit of an encryption layer, you automatically get data protection as part of that encryption, right? Like the part of the encryption is continuous calculating checksums and that decryption on the other end will fail if there's corruption going on. So the workflows we looked at here were even using like HTTP or something like S3 that is still over HTTP if you don't use the S3S. And another thing that's important I want to point out is that Pegasus does not collect this data by default, right? This is something that you have to opt into as a user. And so when SWIP was starting up, we kind of went to a few friendly users and said, "Do you mind if we collect this data on your workflow?" And that's how we get this data. So again, it's not representative of all users across all domains and all that stuff. So here's a few results that we ran into. One is this OSG kink workflow. It's a workflow out of Clemson. And in this case, we ran 50,000 jobs and we saw 60 integrity errors. And the good news here is that those problematic jobs were later just rerun automatically, and the workflow finished successfully without the user knowing even about it, right? So this is an example of detecting and handling this automatically, right? This is how we want this to work. We want the user to have extra confidence in their computation because we're doing these integrity checks, but we also don't want them to, be in the critical path and stop, unnecessarily and things like that. So, but of these 60 errors, we kind of looked at this, and at this point we did this by hand. We went down and we just like grouped and we had everything in a spreadsheet where we could group and sort and things like that. So one input file error at the University of Colorado, we don't know why. We had 3 input file errors on one node at the University of Nebraska. The timestamp was really short between all those 3 failures, 16 seconds. So we think, and because of the locality of this, we think it was one node. Like there was something that happened at node level, like there's a node level cache in this case. And we think that maybe that just, during transfer something got corrupted and then kind of fixed itself. The last point is kind of interesting. There's 56 input file errors, different compute nodes, but they all had the same wrong file. And so this is, the time span was almost 20 minutes. And so we think this was a site level cache, right? Where all the nodes on that site pulls the same file over and over again. They all get the same broken one. And we could tell that they were the same broken one because the checksum, the calculated checksum, matched across these 56 files. It just wasn't the right checksum, right? And again, this fixed itself. By the time that we found and analyzed these errors, we had, the workflow, like the logs and the cache and all that stuff was already gone. So there was no digging deeper here. There was no more information to be had. Another interesting result. So this is a workflow from Georgia Tech, and it's the Veritas telescope. Some simulations for that telescope. And in this case, what we saw is that 0.04% of all transfer failed with integrity errors. And that's about 1 in 2,500 transfers. Again, these are large workflows. We can see here we had 172,000 jobs. And there are some failures, but they're not all integrity failures. The integrity failures are over here, 48, right? And what's interesting about this one is if we go down to lower right graph here, we see them, they happen pretty regularly. When we do analysis on these, we can't, there's no natural grouping, right? They just are totally random. So one of the things that we kind of suspect here is that this is using the S3 protocol against a Ceph object store. And so we really kind of suspect that there's something either in the client or in the Ceph implementation that kind of keeps on causing this. That, like, you know, they are, you know, we keep on hitting the same bug over and over again. It's not often enough for us to be able to actually track it down, but it does happen. And this slide is a little bit old. We should really go back and try, you know, new versions and see if we can narrow this down. The reason we haven't done that, though, is the same as the last slide, that from the user's point of view, this works, right? You know, 1 in 2,500 jobs gets retried, but that's not a big deal. I mean, that's really nothing compared to the normal job failures that we see in Open Science Grid, right? So, so there's really no incentive, or very little incentive, for us to even track this down. And so that's, in some ways, the best case, right? Another thing that we were concerned about, and I think this is something that people, like, that comes up all the time, like even outside SWIP, I keep on hearing this, right, is that, you know, I wish I did integrity validation, but it's just expensive. It takes a long time because of the data size that I deal with. And it turns out that, you know, compared to the time that you do compute on the data, it's actually, I mean, there's really no overhead. We had 3 different workflows here. There's the kink workflow, which an overhead of less than 0.05, the overhead was 0.054%. The second workflow here, 0.068, and then 0.062. This seems pretty even, right? And what we think is happening here is that as data sizes go up, right, the integrity verification takes, like, that increases as well, but so does the compute, right? So data sizes, or like the compute time and the integrity checking time, are both functions of the same data size, and that's why they don't really vary much. You could have something where, you know, you have really big files and you don't do a lot of compute on them, you know, you would see a higher overhead, but as far as we can tell, I mean, it's really not something. And we do have, you can turn off integrity. Like, integrity checking is on by default in Pegasus, but you can turn it off if you think this is a problem for you. So I don't have a slide on this. Oh, I do have a slide on it. Okay, good. Okay. So one of the things that we did in SWIP was that we became really good at detecting and handling these integrity errors. Right? It's like that problem has been solved. But what ends up happening is that when we talk to infrastructure providers and we say, hey, we saw a problem on your site this day, and this is what we saw, here's some little bit of information. And, you know, they want to know more. They want to understand, you know, what else did you see, and what was the environment and all this stuff. Right? They want to have some more detail on where to look and see if they need to take any action on their system. And so there's a follow-on project called Iris. And really what this is, I mean, there's all this, you know, AI and ML and stuff on this slide, but really what the goal here is that with the information that we see on these integrity errors, we should be able to train a model that will do a little bit of root cause analysis for us, right? So remember that slide where I had with analysis by hand, where we said there's a site level cache. We want the system to be able to do that to us, for us, right? That when we see these errors, they should be able to just give us a report and saying, here are the likely cause of these failures. So that's an ongoing project. It's pretty cool. We have, again, we're using the exogeny testbed to build this model and to train it and do the testing. We haven't tested this, you know, we don't have results for anything in the wild yet, but that is, you know, next step probably in this project. So I'm going to stop there and I'm going to go back all the way to the front. So that was the how we take care of protected data. Again, there's nothing in the workflow that helps with things like HIPAA. That's an infrastructure problem. But when it comes to integrity and provenance, reproducibility, those are all features that workflow systems are really good at. So before I talk about the second question, any other questions, any thoughts about integrity? Is David and Tobin, is this something that you are concerned about? Or like, for example, if I leave this one up here, the trustworthy data, is that something that you feel is relevant to your work?
Yeah, definitely. And I think it's something that unless you have a problem with it, you don't really think about it ahead of time.
Right. And I think one of the things that we saw in SWIP is that it's hard to be concerned about something you don't know. It's hard to be concerned about the problem you know that if you don't know you're having it, right? And I think that's true. I think we see that a little bit in this workshop, in the trustworthy data working group as well, is that there's a technical aspect to this, but there's also a lot of kind of education and awareness that is really important that we kind of highlight, right?
Yeah, there was, so we're running an instance of RStudio Server Pro in AWS, and I had a researcher upload some genomic data. So she was trying to run her script, and her script kept failing and saying the file was corrupted. And she's like, no, I ran this on my computer at home and it works just fine. But I had her re-upload the data, and it turned out that the data had gotten corrupted in transit somehow.
Yeah.
It took like a week to figure that out.
And you know, we in the paper we talked about this a little bit, and I think even us as computing specialists, right? We put a lot of trust in our systems. You know, we keep on getting told, hey, you know, this system has RAID and it has an error correcting file system, and you know, we're using all this you know, very expensive network gear, and right. I mean, like it feels like we have a pretty nice environment, and that should be trustworthy in many ways. So so I think it is an important thing is to kind of have that belief that, hey, things can go wrong, right? Like it's not a perfect system, and you just have to kind of keep that in mind.
So Tobin, I was curious, do you remember how big that data set was, where like, you know, the researcher was able to run it successfully at home, but during transit it kept on getting corrupted? Like just a ballpark estimate?
I think she had about 16 files that were about 5 gigs or so each. So it wasn't huge, but it wasn't tiny either.
Okay,
Thank you.
Great. What about David? You do a lot of compute. Are you concerned about this?
Yes, I've actually noticed plenty of times where, you know, data was corrupted in transit, and I spent several years convincing people that no, we do move enough data that even sometimes the checksum will fail in various cases. So
when you do the transfers, well, like, so you still do the physical disks, right? Like from the.
yeah, so we still do physical disks from the South Pole, but otherwise a lot of it is just over the network, various networks.
So have you seen any physical disk issues with that transfer mechanism?
I don't think we've seen any checksum issues with physical disks. It's more been, well, the disk itself is broken. So that's actually a problem.
Yeah. But then do you have a second copy still sitting at the telescope? Not telescope, what's it called? Instrument then?
Yeah, so we do 2 copies, and usually that's okay, but we have actually lost a couple days worth of data because both copies have been either destroyed or misplaced.
Yeah. And I should say, you know, like, I mean, I don't want to paint the too negative picture here also, because, you know, this is becoming a better and like a more and more, like even outside scientific computing, right? Like a known kind of issue. You can see that in some newer file system, like CFS, for example, has, you know, continuously data, like checksumming and error correction in there. So things are getting better, but it's, again, something to be aware of.
Yeah.
So, yeah, go ahead.
And just for the data at rest sort of thing, I mean,
Yeah.
because we have petabytes of data, we've actually noticed occasionally someone reads data a couple years later and it has like, oh, why is this file not computing right now? And you know, it seems like it's truncated because there's a bad bit somewhere. And, and we look at it and like, oh, yeah, the checksum changed. That's interesting.
But you do have checksums of everything, huh?
Yeah.
Right. Very good. Yeah, so this study they did at CERN was the same. I mean, this was obviously one of the either CMS, Atlas, whatever the projects were. It's an older study, 2007, but they, I mean, one of the things is that you know, they found at that point was that 1 in 90 data drives fail, not only fail, but they fail with silent data corruption, right? And this is a pretty high number, I think. Because if you think about, you know, the disk arrays that we have, 90 drives is not a lot of drives. So that's something to, again, also kind of an interesting tidbit.
So David, do you have any thoughts about how to store checksums, or you know, you end up storing the checksums also back on the disk?
So we've done both over the history of the experiment. Occasionally store the checksums next to the files on disk, but we try putting them in databases and using the databases to actually, you know, look at file metadata properties and things like that.
Okay, yeah, thank you. I was just curious because, you know, like people could argue that, you know, checksums can themselves be corrupted, but I think then it's just a false positive failure more than anything. So just wanted to hear your thoughts.
Yeah, so any other questions from Tobin and David, anything? All right. So I'll answer the second question here, the feasibility of workflow system on floating vessels. And, you know, at first I was like, I'm gonna make some slides, and then I couldn't even come up with a single slide, you know, making about this. But in general, there's nothing that stops you, right? But I suspect that this is a hard problem in general, because the problem is, and I, with my CSCOE hat, we've been working with some of these projects for a while. And so when you listen to them, like they have issues like, hey, we spend a little bit of time in the harbor, and then we have good network connectivity. And then when we leave for our trip, we have a crappy satellite uplink that is not even enough for email, basically, right? So so really what this comes down to is, can you run you know, computing environment like let's say Condopool, and things like Pegasus in a total isolated environment? And the answer is yes, right? There's really nothing in neither of those stacks that has hey, we assume an always connected network. So and there might be, you know, I'm not saying it might be perfect, right? Because you might things have like, you know, if you don't have a full DNS, for example, right? Is there something that's going to be upset that you don't that you can't look something up? But in general, there's nothing in Condor, there's nothing in Pegasus that really requires a network connection. So I think this should be fine. I think it's something, obviously, before leaving on a long trip, I would test it, but it is pretty easy to test also, right? I mean, you can easily do a disconnected machine that you can run on, and I suspect, like we've been listening to these projects for a while. You know, they have almost a small internet on these boats already, right? They have, you know, full authentication stacks and web servers and data servers, and like they have all the pieces that we would need for running workflows. I think it's an interesting concept. And actually, David, maybe you are a good person to answer this as well. Like, I mean, you must have something similar set up for local processing at South Pole, right?
Yeah, so we actually have, a small cluster of machines down there that doesn't talk to anyone and gets updated, once or twice a year, and that's it.
Right.
So it's.
Do you remember running into any kind of assumptions in the code that says, "Hey, I assume that I'm online"?
Well, there's a couple of assumptions, especially around how provisioning happened. It was like, okay, well, we assume you can just download this from GitHub, right? Oh, no, that's actually kind of hard.
And is that in the infrastructure or kind of in the user codes that you're talking about?
I mean, that's usually in like the user level codes for the applications that we've written to manage everything.
Yeah. So when you say updating, like when you say patching twice a year or something, like is that YUM upgrades or what are we talking about?
I mean, I don't work with them too closely, but I'm pretty sure it's that a lot of it is that there's some Python software and there's a couple things that need to be compiled from our own code. But I think that the sysadmin has tried to keep the system as YUM and the things that are not the system as outside of YUM.
Yeah. Yeah, I mean, I'm curious. I mean, so you must be running some kind of fake DNS and everything down there, right?
Yeah, so it has its own internal DNS. And all the things, but it's mostly just, if the satellite is up, then yes, okay, you can actually get very slow internet. If the satellite is not up, then you just don't get anything.
Yeah, the vessels have they talk about, for example, quotas, like each user get a little quota where they can, email family and keep in contact and things like that. So obviously you don't want to burn that quota on running compute jobs. So that's one thing. Something else I was going for, I forgot it.
So David, do you know if you guys have been looking at Starlink to get better internet, or it won't be covered, like South Pole won't be covered?
So I've looked at it a little bit. I don't think South Pole is covered yet. Maybe whenever they finish their network, it will be. But that's definitely been interesting to look at, like what new satellite technologies could we do to get higher bandwidth? The Iridium Next stuff was actually really useful because the older Iridium is very, very slow versus the newer stuff is actually, we've seen a little bit faster connections for that.
Yeah, I read recently Starlink has reached 60 Mbps in their tests at least.
Yeah, except it's still within a very small latitude in the north. So.
Yeah, I was going to say you have blackouts as well, right? I mean, there's times where you can't get to the satellites, right?
So with Iridium, we have 24-hour coverage, but that's you can do a login that's very slow, but it works. But we don't transfer any data over that, except for the real-time alerts go over that, but that's very, very small amount of data. The actual bulk data goes whenever one of the large geosynchronous satellites is up, which is 4 hours a day.
Yeah, I know the vessels, it's not really a problem of capability, but it's a problem of cost, right? I mean, obviously, that's like they could spend as much money as they want on an uplink, and they don't really seem limited except in money spent. But then they have things like if they are rough sea and stuff like that, like they can't stay connected the same way. So maybe they have a similar problem. I don't know. The point is, I don't think compute is anything different than running a compute environment in general. I think that should be fine. Anything else? Let me go and see if I had any other slides. I mean, I added a lot in here. To talk about. Oh yeah, we can talk about this a little bit. So currently, the Pegasus team is working on Pegasus 5.0, And Pegasus has been around for a long time. And this is a pretty big upgrade for us, where we are, we're moving to Python 3, but as part of that is a brand new API. And so that is a big change. There's even more kind of like workflow generated by code. But at the same time, we made it simpler, right? So we're talking about zero configuration for condo pools, all the data management improvements under the hood, and new documentation. So we're pretty excited. We have a beta 1 out. It's probably not for 3 or 4 weeks now. We don't have a date here yet, but it is soon. So that's exciting. If you want to start using Pegasus, I would start with 5.0. I would not learn 4.9 and then go to 5.0. What else? I can talk about this. I mean, I guess this is a little bit related to what you were saying, David, about, assumptions that you kind of pull stuff as you go. Containers is one of those examples, right? You have a workflow, and the compute environment, or like the actual environment that you want for your jobs, is a container. And anybody with a good network, well, all we do is we just say, we tell them what Docker container or Singularity container to use, and it's just pulled automatically. So this is something like you have to kind of think about beforehand. And Pegasus handles this case fine. You can just pull the container and put it locally, and then point to that. We don't require, obviously, Docker Hub or Singularity Library, but it's stuff that you can use. So again, if you just test this before leaving on your journey, I think you're fine. Integrity checking, we talked about that. Okay. I think that's it. Well, thank you for attending. It was a small audience, but it was great. So thank you. And Tobin, David, you know where to find me if you have any questions. And thank you for participating.